runs things a little bit differently. It's going to run kind of the same as what we did before. So as far as hypotheses go, we have a null and alternative hypothesis. Now, a typical hypothesis test for the difference of two proportions is one where we assume there's no difference. So we start with the assumption that there's no difference between the two groups we're examining. Now, when you write these hypotheses, there's two different ways you can write them. Each kind of has their own pros and cons. Okay? And we'll talk a little bit about those as we go. So the null hypothesis is one of these two versions here. So you can write it as, when we take P1 minus P2, we get a difference of 0. So that's the null. There's no difference between the proportions of our two groups. The other way to write that is, instead of writing this as a comparison to 0, you can just say, well, if I add the P2 over, that means P1 and P2 have to be identical. If I'm going to subtract two numbers and get 0, they had to have been equal to start with. Okay? So when you write your null hypothesis, you can write P1 minus P2 equals 0, or you can write P1 equals P2. Now, as far as the advantages of each, when you write it this way with the subtraction, first it reminds you that you're working with subtraction. So you're subtracting the two proportions. The other thing is that you recognize our main goal is 0. If 0 is in the interval, if we're looking there, or if 0 is going to be what we're looking for as far as a difference. Okay? So it kind of tells you exactly what you're looking at in the problem. The advantage of this one, the P1 equals P2, when we write our alternatives with that, it makes it easier to plug into your calculator when we look at our test, because the direction that we go, the arrow's easier to see which direction we want to go. So it's kind of a whatever preference you prefer, which version you want to use. Either one would be accepted. Okay? So when we write our alternatives, we're going to look at an example here. When we write our alternatives, it's the same as before. Either we think we're going to get less than 0, greater than 0, or we might just be interested in, is there a difference? Which means we go not equal to 0. So everything about the hypotheses is pretty much identical to before. It's only now we have to account for two groups that we're comparing.
So if you use the P1 is equal to P2 and then the second hypothesis, you're going back, comparing it to 0 instead of each one?
So, well, basically what you'd be looking at here, so if this was the way you wrote out your null, your alternatives would be P1 minus P2 is less than 0, or P1 minus P2 is greater than 0, or P1 minus P2 is not equal to 0. Those would be your options.
So then, like, the other one would be...
Yes. Okay. So if you write it in this format, this is what you'd end up with. And when we go through the process in your calculator, one of the things we'll show you is when you get to the point where you select what direction you're going, you're going to see this notation. So if you write it this way, it's easier to find exactly which one you want here. Okay? Now, as far as the directions go, even if you write it this way, if the arrow is pointing left, you want your arrow on your calculator pointing left as well. Both of these are the exact same conclusion. Okay? Yeah, no matter how you interpret it, it's always going to be the same. Mm-hmm. It's just a preference as far as which method you want to use for comparison. So the arrows are going to point the same way regardless, or they're not equal to, so it's fairly straightforward either way, but you'll see it both. I used to like this one better, but recently I started more liking this one. It just reminds you of the subtraction. It reminds you that 0 is the value in question. So it just gives you a little bit more information. Okay? All right, so for an example, researchers designed a survey to compare the proportion of children who come to school without eating breakfast in 2 low-income elementary schools. An SRS of 80 students from school 1 found that 19 had not eaten breakfast. At school 2, an SRS of 150 students included 26 who had not had breakfast. More than 1,500 students attend each school. Do these data give convincing evidence of a difference in the population proportions? Okay. So, in a hypothesis test, the steps for this type of hypothesis test is exactly the same as the steps for one sample proportion or mean test as well. So our first step was always to write the hypotheses. So we always get the hypotheses first, then we proceed from there. So we just said our null hypothesis should be that the difference is 0, so that there's no difference between the proportions, right? So our null is going to be that P1 minus P2 is equal to 0. And we're okay using P1 and P2 because we're calling them school 1 and school 2. So it should be pretty straightforward to keep track of what we're working with. Now, for our alternative hypothesis, what are we doing? Not equal to. So in this case, they said, is there evidence of a difference? So we're not trying to specify a direction with that. It's just saying, is there a difference between the 2 schools? So, for the appropriate hypotheses, the null would be that P1 minus P2 equals 0. The alternative then is that P1 minus P2 is not equal to 0. In words, that means the proportion of students who had not eaten breakfast at these low-income schools is the same for our null. The proportion for both schools is the same. Our alternative is that the proportion between the 2 schools is different. Okay? So in words, that's what we're discussing. Now, this would happen to be a not equal to. In some cases, we might have an inclination as to which group might be higher or lower than the other. So if they said, for instance, on this one, that we think school 2 has a higher proportion. So we want to test to see whether school 2 has a higher proportion than school 1. Our null isn't going to change. We're still going to assume no difference. But when I go to do my alternative, if I do P1 minus P2, and we think P2 is bigger, then that means this difference should be less than 0. So one of the things that you have to make sure you account for when you set up your alternative hypotheses is the direction in which you subtract. Again, you can choose the direction. For this one, we chose 1 minus 2. For that same scenario, if we think 2 is larger than 1, if I reverse this order, P2 minus P1 is still 0 for the null. It doesn't matter what order we go in, we should still get 0 for that null hypothesis. But if I do 2 minus 1, and I think 2 is bigger, then that would make it greater than 0. Okay? So the order you go is going to dictate which direction you go for your alternative. Okay? Now that's only in the cases where you're assuming a direction on the difference. When we assume one is higher than the other. Is everyone okay with that? All right, so next part, once we have our hypotheses written, we would check our conditions. The conditions for running a significance test are exactly the same as the conditions for constructing the interval. We need separate random samples, so independent random samples chosen, or we have to have 2 groups from a randomized experiment. We need to make sure that both groups represent less than 10% of their respective populations. And we need to make sure that NP and NQ for both groups are at least 10. Now, one of the things that's a little bit different from this hypothesis test compared to the hypothesis test for one sample proportion. If I ran a test for one sample proportion, they told me a proportion to assume true. they said the true population proportion is believed to be this. We want to know if that's the case if we found this sample proportion in the problem. So we did NP and NQ because we had a population value to work with. Now, in these problems, if I'm looking for the difference of two proportions, they won't give us the true values. If they told us what the true proportions are, we would know just from that whether there's a difference or not. Take P1 minus P2. If it's not 0, there's a difference. Okay? So we don't know those right off the bat. So one of the things that you want to add to this, because it's a typo, I forgot to switch. This needs to be NP hat and NQ hat. So whereas a test for one proportion, we were able to use the parameter value, here we don't have those parameter values. We're only looking at whether there's a difference between the two. We don't know what they actually are. So we have to use our sample proportions to work through our NP and NQs. Okay? So, back to our example here. If we check the conditions, do we have separate random samples? Yeah, so they're two completely separate schools, both low income. We took an SRS from each, so we're separate random samples. Okay? The next one would be the 10% condition. So, would 80 students be less than 1,500 plus? Or less than 10% of 1,500 plus? Yeah, and that's when you could physically check. You take 80 divided by 1,500, you should get something less than 10%. Okay? Now, if I check 150 students out of 1,500 plus. Now, if I did 150 divided by 15 straight up, what would I get? 10%. And I need to be less than that, right? So, if I get exactly 10%, what saves me here? They're saying more than 1,500 students. So the fact that more than 1,500 students are there, even though I would get 10% by dividing these directly, there's more than 1,500, which means I'm going to be just under 10%. Okay? And then as far as NP and NQ go, in this case, they basically told us the information we need. So NP1, 19. So our sample proportion was 19 out of 80. So we have 19 successes, 61 fails. For the second group, 26 out of the 150, so 26 successes, 124 fails, all of which are larger than 10. Okay? So same conditions as we've always checked. We good so far? Okay? Now, when we run our hypothesis test, the next thing we would do, we've stated our hypotheses, we have checked our conditions, so the next thing we have to go for is our test statistic. So what is our z-score in this instance? Since we're talking proportions, we're talking about a normal distribution, we're talking z. So we would need to calculate a z-score. Now in order to do that, I would need to take my sample value minus the mean of my distribution divided by my standard error. So one of the things that we have to talk about here, this is a pretty significant change from previous tests and intervals. Because our null hypothesis is that there's no difference between the proportions. So look at our sample, or look at our standard error formula. It's PQ over N for group 1, PQ over N for group 2. But our null hypothesis says that P for group 1 should be identical to P for group 2, correct? Now, if I'm going to have the same proportion for group 1 and group 2, then what should that mean about each individual standard deviation? It should start off with the same, okay? So what's happening here, if there's truly no difference, which is what we assume at the start, the standard deviation for each proportion should be identical because we're starting with the same p-value. Okay? So what this does is allow us to combine, or what they call pool, our counts. So what we need to account for now is that we're going to take the information from both groups and combine them as if they were one. So when we go to find our standard error, the first thing we need to do is figure out what our pooled proportion would be. So that would be the number of successes from group 1 plus the number of successes from group 2 divided by the sum of the samples. So we're going to put it all together into one proportion because we're saying that overall it should be the same for both groups. Okay? So what that means then as far as standard error. When we want to calculate the standard error for a hypothesis test, and something you want to make sure you definitely put down here, this only works on a hypothesis test. Do not ever pool for an interval. Do not pool when you're running an interval. In a hypothesis test, we're making a very specific assumption that there's no difference, which is why we're able to pool to give us some stronger information. So once we have this pooled proportion, we use that for our P and Q for both groups. So P for group 1, Q for group 1 is the same now as P for group 2, Q for group 2. Now, the other thing to note here is that we still divide by each separate sample size. So once we have our pooled proportions, we're still going to divide by the original sample sizes of each group separately. So P pooled, Q pooled over N1 plus P pooled, Q pooled over N2. That's going to be our standard error formula. Okay? So, for our example, if we want to calculate our standard error, which is part of what we need to find our test statistic, we would pool our proportions. Okay? Now, it looks like a lot of work here, but you guys will be able to plug stuff straight in. I'm just showing you every single step throughout. So for the proportion, the pooled proportion, we take the number of successes from 1 plus the number of successes from 2. So 19 from group 1, 26 from group 2. That goes on top. Then you add the sample sizes together, so the 80 and the 150. So our pooled proportion would be 45 out of 230, which as a decimal would be 0.1957. Now, when we come down to a standard error, this is our new p-value. So 0.1957, I just rounded to 0.2 for the sake of this example. So 0.2 times 0.8 divided by sample 1 plus 0.2 times 0.8 divided by sample 2. So once you have that pooled proportion, you just use it for the P and the Q for both sets. And then just divide out by each individual sample size, so 0.0554. Okay? So after you check your conditions, next step would be to pool. So calculate the pooled proportion, calculate your standard error. Once you've done that, it's time to calculate Z. And we calculate Z the exact same way we've calculated Z from chapter 2 and on. Sample minus mean divided by standard deviation. Now, for our particular problem, the statistic would be the difference of the sample proportions. So based on our sample proportions, what difference did we calculate? Our parameter is going to be what? What are we assuming the difference to be? 0. So in this type of problem, the statistic is just p hat 1 minus p hat 2. The parameter will always be 0. The only way that 0 would change is if, for some reason, your null hypothesis had a specified difference. Now, as far as the problems we are going to be concerned with, our null is always going to be that there's no difference. So for our purposes, that value is always going to be 0. So you subtract p hat 1 minus p hat 2 and get that difference. And then subtract 0, divide by the standard error that was pooled. Once we have z, the next thing would be to calculate when we run a hypothesis test, what's the ultimate deciding factor in how we reject or fail to reject? P. So the next step would be to find our probability. So when we calculate our test statistic here, our z-score would be calculated by taking p hat 1 minus p hat 2, so 19 out of 80 minus 26 out of 150. I wrote it in fraction form here. You could find the decimal versions and do the same thing. Doesn't really matter at this point, okay? So I choose that, minus 0, divide by the standard error that we calculated, 0.0554. So we get a z-score of 1.16. Once I have a z-score, if I want to calculate p, I need to use the table or, not inverse norm. T would be if we had a t-distribution. We have z, which would be normal CDF. So you use your normal CDF. We calculate the probability that z is greater than 1.16. We always go to the tail. So since this was a positive z-score, we need to go greater than, because we're looking at the tail. Now, the other thing, so we calculate z greater than 1.16. Why am I multiplying that by 2? Because the alternative was not equal to, which means once I find one tail, I need to double it to find the other. So we get a p-value here of 0.2460. And again, that comes from your table or from your normal CDF function. So with a p-value of 0.2460, what would we conclude? Yeah, it doesn't matter what alpha level we have. We're going to fail to reject because p is going to be larger than the alpha we choose. So if we fail to reject, that means there's no convincing evidence that there's a difference in the proportions. Okay, so there's no convincing evidence that there's a difference in the proportions. Okay. So, same process, the only difference is that middle step where you have to calculate your pooled proportion and your pooled standard error. So here are the problems I want you to work.